It's a great pleasure. It's a great pleasure to share our ongoing work on this platform, and it's a joint work with my former PhD students, Haojie Bao. He is a postdoc in Nankai University, and supervised by the Professor Changliang Zhou, and also this joint work is with my PhD students, Yang Hu. And this work is about how to make smarter or safer decisions and these uncertainty sets by bridging two powerful frameworks about the conformal prediction and the conditional robust optimizations. And here is our roadmap, and we will start with the background and motivation, and then move to our method Quarks. It is aimed to implement the contextual selection of uncertainty sets. And then we will see how well the proposed method performance in the numerical studies. So let's begin. And in practice, we usually make decisions by minimize a loss function. We can denote it as this phi. And for example, for the portfolio optimization, and assume Y is P stock returns, and Z is the decision of portfolio weights. And when we want to make decision by minimize the invest risk, and also for the medical diagnosis, a doctor wants to decide a treatment is this day to minimize the patient's harm based on the true diagnosis. That's why. And the fact is, when we decide the true Y is usually unknown. So so in these cases, when we will use a machine learning model such like this HET-F to predict Y from the covariant X. And like this one X-ray image, we will input this covariate X and use a machine learning model. We'll get it predictor. Its predict point, we will denote it as this HET-Fx, and then we will minimize this loss function to make the decision. This is the predict then optimize framework. And this prediction then optimize is very popular, and but it is very risky because the smaller prediction errors can lead to the disaster decisions. So let's see the medical example. Assume we have a new patient. He takes his X-ray image, and with this X image, we will fit this X-ray into a machine learning model, like this CNN model, and then we will get it. We'll get its predicted probabilities. So like this one, we will have the 60% for its normal, and 40% for its COVID-19, and 0% for other disease. And we would like to predict the most likely label is the normal, right? So we will denote this HET-F is the normal. And then we will use a predict then optimize strategy. Based on this loss function, we can say we will choose the treatment, the smaller one is zero, is no action. So our decision is no action. But we have the 40% for COVID-19. So if the true label is COVID-19, we will take this no action treatment will cost 10. It is very risk for this patient. So this highlights a critical flaw with the predict and optimize strategy. The decision based on a prediction point can be very dangerous. It's too risky. So we need a way to robustify the decision against the prediction uncertainty. That's where the conditional robust optimization CRO works. So instead of trusting a single prediction point, it builds the uncertainty set UX, and that includes the true label Y with 1 minus alpha probabilities. We call this is the marginal coverage. And then we will get the decision by solving these minimax optimization problems. This ensures the decisions are robust to the worst cases over this uncertainty set UX. And this is a very popular framework, and many researchers have aimed to solve this problem. And over the decades, there are a lot of efficient algorithms for this CRO problem when this uncertainty set UX is given. And with this program, this framework, let's see the medical example again. So now we use the CRO rule. Instead of predicting the normal point, we will construct an uncertainty set. This UX will include the normal and the COVID-19. And now we will solve the minimax problem. From this loss matrix, we can see the worst cases, for the no action is 10 if the true label is from the COVID-19, and the worst cases loss for the additional testing is just 6, even the true label is the normal. So by minimax this optimization problem, we will choose the treatment is the additional testing, satisfy a little efficiency for the huge risk reduction. That means the CRO can make a safe and robust decision by using this uncertainty set. And that also means its success relies on this uncertainty set. So if we have a well-designed uncertainty set, it will perform well, right? So how to build this uncertainty set? Usually, we want to this uncertainty set satisfy the marginal coverage property is like this one. And the traditional methods, we will assume we know the distribution of X and Y, or at least we will have a very nice parametric model to build the uncertainty set. But nowadays, the Y could be high dimensional, such as a vector of 100 stocks, or the pre-trained model might be very complex, like a black box model, like the CNN or deep learning or something like that. So in such cases, the distribution assumption will fail. So how to build this valid uncertainty set satisfy this marginal coverage? The answer is conformal prediction. This is a way to build the model-free and distribution-free uncertainty set with theoretical guarantees. Conformal prediction has attracted much attention in recent years. There are a lot of amazing works. The Michael Jordan, a titan in statistics and machine learning, said conformal prediction ideas are the answer to the uncertainty quantification. He thought it's the best he has seen, simple and generalizable. So let's see what's the conformal prediction. Here we will use the hat F as it's a pre-trained model. It can be any model, the simple parametric model or the complex black box model will be fine. And also we need a label data. It has X and also has Y, and also we have a new unlabeled data. We just have its S. We want to build the uncertainty set for this new X. And the conformal prediction also needs a score function, this S. It measures the distance between the true label Y and its prediction hat Fx, such as this box score and this ellipsoid score. So the classical conformal prediction will set the uncertainty set like this one, and like this one, and this S is the score function, and the Q is the sample quantile by calibrating the historical data. And Lei Jing and Wolfman in their JASA's paper has proved if the new data and the historical data are IID, the true Y will be fall in this set with more than 1 minus alpha probability. it is a finite sample coverage. That means this conformal uncertainty set satisfies the marginal coverage with the no distribution assumption and no model requirements. It just needs the data on ID. So this is a very powerful framework. But our question is, different models or different scores can use conformal prediction to build different uncertainty sets. So for example, we have several hospitals and they use their own data to train the model. And that means we have several models, and also maybe one hospital just to train different model. It maybe can train a simple linear model, maybe train a SVM or a CNN model like that, or maybe they just consider different score functions, maybe this box score or maybe the elliptical score. So that means each generated its own uncertainty set. We denote it as this U theta x, then theta belongs to this capital theta. Capital theta can be multiple source data sets or maybe different models or different scores. And we know this U theta x have the different shape and or different size. So the question is, when a new patient come, he has his X-ray image, and which is the best one uncertainty set for him we can use for the decision making. So this is where we want to come in. So let's have a short summary. The conformal prediction could construct statistical valid uncertainty sets for different scores or for different models, but it ignores the downstream decision task. And the conditional robust optimization can get a robust decision for one given uncertainty set Ux, but it needs the Ux is well specified. So existing work treats these two separate steps. CP focus on the fact coverage, and the CRO focus on optimizations. So neither answers which U theta x could minimize the decision loss for a new patient, for a new covariate x. So that's our aim, to unify these two words to select the best one dynamically based on the context x. So we call our framework as this conditional robust optimization with the conditional selection. It's shortened by the CROCS. So formally, we will have different, we have multiple candidate uncertainty sets by the conformal prediction, and all of them will satisfy the marginal coverage. And based on each uncertainty set, we can build its own decision rule. We will by minimax this optimized problem, the CRO problem, we denote it as this ZX U theta. And our proposed CROCS makes two things. The first one is to find the optimal theta star that minimize the conditional expected loss for one given x. It means for each patient x, we can pick the optimal uncertainty set for him that minimize the expected actual loss. And with optimal theta star, we can build the optimal uncertainty set U theta star x. And with optimal uncertainty set, we plug into the CRO problem. With it, we can get the optimal decision. We can denote it as this Z star x. So this is the key idea we want to do. Of course, the theta star, we can't get it because we don't know the conditional distribution of y given x. So in practice, we have to use the label data to estimate it. So if we denoted this estimated as this hat theta nx, and with this estimator, we will get the final decision rule will be this hat z hat z nx, and we can expect this hat z is not optimal because this hat theta is not the true one. So with this hat z, our question is how to say this hat z is a good decision rule. And here we need to consider two metrics, the robustness and these asymptotic optimalities. So first, let's see the robustness. Robustness means a decision rule, this z will be called the robustness if the ground truth loss achieved by this decision is this y is true, and this is the true loss, and would exist the worst cases loss when we given the uncertainty set ux. It is from the CRO problem. If this ground truth loss won't exist, the worst cases loss when we given the uncertainty set will not with the probability 1 minus alpha, we will call this decision is robust. And further, we will also call the decision rule is asymptotic robust if the probability 1 minus alpha the probability converge to the 1 minus alpha asymptotically as the data grows. And this robustness is a general goal of the CRO problems. And many works studied this property for one given uncertainty set, such as this Bursey mathematical programming paper. And besides the robustness, we also define a new metric for the selected decision rule, asymptotic optimalities. So if it is when as n go to the infinity, the decision, the gap between the loss based on this select decision hat z and the loss based on the oracle z star, the gap between these two will vanish. This is the new metric. And it means we hope the select decision will converge to the best possible ones. And these are two key goals we want to achieve. And next, let's see how to implement our quirks in practice to achieve these two goals. So the step one is to build conformal uncertainty sets. So here for each candidate theta, we will compute their score functions and then build their conformal uncertainty sets based on the n calibration data. And with this uncertainty set u theta, we will build the corresponding CRO decision rule. We denoted at this zx u theta. So we will have capital theta's CRO problems. So the step two is approximate the conditional loss function. And here we want to find the optimal theta star. It works best for a new covariate X. So here, firstly, we will, for the historical data, we will compute the decision based on its uncertainty set. We will denote at this the xi u theta. This xi is the historical data. And then we need to approximate this conditional mean. And here we need to note this conditional mean is just a one dimension. So many works can use to estimate it well. And here we will use the kernel method, this NW method, to based on all of the historical data, include their y, x, and also their corresponding decisions. Use all of them to build this NW method. And here, this Wix is a weight to measure how close the new x to the historical data xi. And then with this conditional mean, we can minimize this term to find the optimal one. We denoted as this theta nx, and this is our choice. So intuitively, we will learn this best data from the historical data, and to use that data will look like the current ones. And the step 3 is to perform the selection and then make decisions. So we have get best theta's estimation, this hat theta, and we will plug in to the conformal uncertainty set to get the hat ux, and then plug into the CRO problem and solve this minimax problem to get the final decision hat z. And this is the whole framework. And most of the CRO problems are considered this is a convex and can be efficiently solved by many well-studied algorithms. So in our framework, we also consider they are convex, and to get the final decision hat z, we just need to solve this capital theta times n+1 CRO problems. And here is a typical example. When we worry about the individual decision rule is very costing for each new patient, we will to make a individual decision, right? And in practice, it seems like very costly, right? So in practice, we can consider these group conditions. That means the covariate can be separated into different groups. Imagine the patients can be grouped by their age or their symptoms. In such cases, our Cox framework can learn the optimal uncertainty set for each group. So the optimal theta star, we can define it as this one, and then we can estimate it by this weighted function. So for a new patient, we just need firstly to judge which group he belongs to, and then build this uncertainty set hat UKX and solve the CRO problem to get the final decisions. And here's the full picture. For new covariate, we want to implement the contextual selection and to get the oracle theta star and the robust optimization get the oracle decisions. But this theta star we can't know. We can't get it because it is unknown, right? And so we will consider use the historical data to estimate it. And this xi, yi from 1 to n is a historical data, and we use it to get the conformal uncertainty sets and get the corresponding decisions. And based on this data, we will have their true label and their decision, and we will use this historical data to use the kernel method to approximate the conditional mean and to select the best hat theta, and we will plug this hat theta into the minimax problem. We will get the final decision, this hat z. And we also provide the theoretical guarantees for the proposed method. The first one is about the coverage. Because we data-driven selected as the uncertainty set, it means the selection will bring some extra random, and it leads to the selected uncertainty set will lose the finite sample coverage. So it's a common thing we can see in the selective inference due to double dipping data. In our theorem, we have shown this with this selected hat U can achieve the marginal coverage guarantee asymptotically. And this extra term is based on the sample size n, and also based on the size of candidate models, the capital theta. And with this same one, we can easily get the decision rule and achieve the asymptotically robustness. So this result is distribution free and model free. And we only just need the data, the historical data, and the new data are RID. And to get the optimality property, we need some assumptions, and such as the density function for x, and also need some regularity conditions for the loss function phi, and also for the score function and the CRO solutions. And these conditions are very mild and usually has been seen in the CRO community and the conformal prediction community. So due to the time limit, I skip the details and just show you the result. So with these assumptions, we have proved the proposed decision has they satisfy the asymptotic optimality. That means as the n go to infinity and use the suitable bandwidth for the kernel methods, we can the loss based on this selected decision is very close to the oracle ones. And as I just mentioned, we just get the asymptotic robust result. If one still want to get the finite sample robust decision, we also build the four clocks. It uses a four conformal prediction strategy to calibration the selected uncertainty set. So the four conformal prediction is unlike the split conformal ones. It updates the quantile by recomputing the scores for each given y, and by the exchangeability, the four conformal also has a marginal coverage, and it is very computational cost because we need to search every y to find this Q theta y and to build the uncertainty set. So with this idea, we also built our four clocks, and it is recalibrating the uncertainty set. So the key idea is for each given y, we will build the uncertainty set like this one. And for this each y, we will to find the best theta for him. We denoted as this had theta y, and then with it, we will build the final uncertainty set x as this one. So we will select this one, and we can get the result is this four clocks uncertainty set ensures the exact finite sample or marginal coverage, and correspondingly, the decision will achieve the exact robustness in a distribution and the model-free way. Okay, let's see the performance of our clocks and the four clocks in numerical results. Because our method is the first work to implement individual selection in robust decision, so we just consider the randomly selected model as a naive baseline. So we will compare the average loss and the coverage rate of these three methods. And here we consider the score is the elliptical score and set the target level as 0.9. And for the first setting, we consider the overlap group setting. And here we trained four different random forest model based on four group data. And these four group data are overlapped. So these the four models, and we can see the model are very different. So we can expect the uncertainty set from these four models will perform differently. So here, over different sample size, we can see both the clocks and the four clocks lead to much smaller loss, and also the clocks lead to a little inflated coverage rate, as I just discussed in the sim one. But it is still very close to our target level 0.9. And this plot shows the results over the target level alpha. Here, our quarks is a red line, and the 4 quarks is the green one. We can see in cross order settings, our proposed method perform robustly and has this smaller loss and compared to this naive one. And also the 4 quarks can yield exact coverage rate as expected. And we also consider another setting, the covariate shift setting. Here we build for different models based on different distributed covariates. And here is the difference among these 4 models. And this is the results over different sample size. Still, we can see quarks maintains the low loss and has the very close the coverage. And also across the target level, quarks and the 4 quarks perform the best and makes the robust decisions. And at last, let's come back to the medical diagnosis. So the here we consider a real data it from the COVID-19 radiographic database. And here the input is an X-ray image. It's 3 times 224 times 224 array. And the Y is the true disease, and the decision is the treatment. And the loss function is the loss matrix, as I just mentioned at the beginning. And here we have trained the 6 CNN model based on different data. And this is the result. And the red is our quarks, and we can see the red one results in the lower loss, and compared to this naive one, and also the coverage stays on the target level, and that means the quarks can select the best model for each patient and can help doctor to make the safer decisions. And to quick summary, in this work we propose the quarks, and the quarks bridge the 2 powerful framework, the conformal prediction and the conditional robust optimizations. So for conformal prediction, we select the optimal conformal prediction uncertainty set from the downstream task of the decision making, and from the CRO view, we have make the optimal robust decision with a model-free uncertainty set. And our proposed quarks is optimal and robust and data efficient. And it could balance the safety and the efficiency for the making decisions. And actually, this work is ongoing. We just found that this problem is very interesting and important. And also, we have a lot of details need to be discussed in our work. And to end this talk, I want to discuss 2 future targets. So here, we built the uncertainty set that satisfies the marginal coverage. So if we aim to make the individual decisions, a better way is to build the uncertainty set satisfies the conditional coverage. So there are a lot of conformal works to construct the conditional sets in different views, but how to aggregate them to the decision-making problem needs the further studies. And also, we assume the complex model is pre-trained. So here we just need to select one of these pre-trained model for the downstream decisions. Whether we can build an end-to-end framework to learn the model by minimize the CRO loss functions. So it's very interesting, and we are still thinking how to make it. And if you have any ideas, I'd like to discuss with you. And okay, and I think I will stop here. And thank you very much.